All right, so 2.2 intramolecular forces, intra-forces. So these are like bonds, not intermolecular forces that are between molecules. These are actual bonds. They are stronger. And we'll also be looking at the potential energy, okay, which is the energy that's released in order to form the bond. And that, of course, correlates with how much energy you have to put in to break the bond or overcome that force of the bond. So you're going to interpret and draw potential energy versus the distance between atoms graphs. Compare the bond length, bond order, bond strength, and bond energies. Use Coulomb's law to compare the strengths of ionic compounds, relate the strength to physical properties. All right, so how does a covalent bond form? Interaction here showing you of two hydrogen atoms. Now, the first diagram up here is showing you they are far apart, okay? The electron density of the cloud, like they're not even close enough to really interact. So that's one thing. Then they get closer so that there's some interaction. And eventually they get to a point where the electron clouds have an optimum distance between them. So this is what we would call the bond length, is the optimum distance. Now, the nucleus of the one is going to attract the electron of the other. The nucleus of one is going to attract the electron of the other. Of course, this is hydrogen, so there's one proton, one electron. So this is the Coulombic attraction that I'm talking about here for covalent, and that's why the electron clouds overlap in it. They are sharing electrons, essentially. Whereas in the ionic category, remember, it's a complete transfer, and the electron clouds don't really overlap. They stay as separate entities, but they attract to one another because of the charges. So different interaction here. Now, as the atoms get closer together, they establish this optimum distance. And the optimum distance is really about maximizing the attractive forces, which are the nuclei to the other electrons of the other particular atom's cloud. And they minimize the repulsions because you have the electrons repelling each other and then you have the nuclei repelling each other. So you have two sets of forces going on here. You want to maximize attractive, minimize repulsive forces. And that's what establishes the optimum distance, really, is that fact. Where is it best for attraction and worst for repulsion? And we use this, or they draw out this internuclear distance graph and the potential energy on here. So we have our potential energy versus internuclear distance. The potential energy is on the y. And as you know, they are all negative numbers because when you form a bond, forming is warming, energy is released. So the negative is really only telling you that it's being released and it's exothermic process. That number, though, of how much is being released is also how much you would have to input to break the bond. So that's the magnitude, that's what we would call the bond energy. They draw this curvy little graph here to show you kind of a couple different things. Over here, atoms are too far apart. They are not going to interact, right? Very well. Now they start to get closer. There's some interaction, but they haven't maximized the optimum distance, and they are, the best attractive and repulsive forces at that point. So the energy is still a little bit higher. And remember about chemistry, the main overarching goal of everything is to get to the most stable complex that you can get. And that is always going to be at the lowest energy that you can be. So releasing more energy puts you at a lower energy state. So that's the whole point of this, is to get to a lower energy state so you're more stable, or that the atoms are more stable. Then here's 3 is showing you the bottom of the dip here, and that is where the most energy is released, and that is the most optimum for the distance between them, where it maximizes attractive forces, minimizes the repulsive forces. If you go too close together, which is number 4, that one shows you that they are too close together, and it actually causes more repulsion than it does attraction, and that's why the energy goes up quite a bit. As you can see, it steeply goes up at this point if they're too close together, okay? So the bottom part where it dips is where it's optimum for its distance for the bond length, and it's also where the attractive forces are the greatest and the repulsive forces are at minimum. Okay, so that's the best deal there. Once again, I'm not going to show the entire thing, but I want to show you an idea of what we're talking about when we're talking about the attraction repulsion. And if you want to watch the entire bond formation video, you can. It's really good. But I just wanted to show you a couple little segments of that. Okay, so here it's kind of showing you the setup for, you have atom A and atom B. Okay, attractive forces are held between them, and it's going to start showing them. So that particular one right there, this nucleus of B is being attracted to the electron on A. That would be an attractive force. Then it's going to show you the opposite there. I'm sorry, yeah, nucleus of A attracting B this time. Okay. Now, the two protons here are going to be repelling those nuclei, and then the electrons are going to be repelling. Okay, as you can see there. So, what you're going to be trying to do here, I'm going to move it along a little bit so you can kind of see. So here is where, if we're looking at our graph, a little further along here. Let me see. Equilibrium of the internuclear distance is reached. So you are maximizing these right here. Those are being maximized. And you're minimizing these. Okay? The green are the repulsive forces. And then you establish that here at the bottom of the curve, which is also right here tells you the bond length or the internuclear distance. So you know how much energy is released over here on the Y, and you also know what the internuclear distance is, the most optimum for the maximizing of the attractive forces that show the X kind of deal, and minimizing these repulsive forces, which are the parallels. Okay? Like I said, you can watch the entire video if you want to, but I think it's really good representation and showing you how that's going to work with the covalent bond where you're overlapping the electron clouds. All right, so optimal internuclear distance achieves the lowest overall potential energy of the system. That energy is being released because the bond is forming. Forming is warming. You're sending it out. It's exothermic. And that also puts it at its lowest energy state. Lowest energy state, most stable arrangement for that particular bond. Here, as you can see, this is for hydrogen, I believe. As you can see, they're telling us that the bond energy is going to be 436 kilojoules per mole. And that would be to break up the bond. You would have to input that amount of energy. It's also showing you here 74 picometers is the optimum length between the two atoms. Okay. Bond energy is the energy required when breaking the bond. It's also the same magnitude of the energy when it's released forming the bond. The magnitude is the same, the sign is different. Remember, the sign's just telling you it's leaving the system. If it's forming is warming and your energy is being released, that's exothermic. And if it's positive, the energy is being absorbed in, like say to break the bond, that is going to be endothermic. Now, let's talk about bond types. The number of bonds between atoms, which is dependent on how many electrons they share, is going to be what we call bond order. A single bond shares one pair of electrons, that's 2 in total. We usually represent it with one line, and that has a bond order of 1. Double bonds share 2 pairs of electrons, which is a total of 4. So the bond order is 2. And a triple bond shares 3 pairs, which is a total of 6 electrons. The bond order is 3. Now, this is pretty normal, single bonds, double bonds, triple bonds, that idea, and we'll get into drawing the Lewis dot structures in the next section of notes. However, do understand and maybe recall a little bit from some of the ones that you did last year that some structures, they have resonance where they equally distribute a bond over multiple bonds. So the bond order doesn't always have to be a whole number. So if they are sharing and one particular bond between them, like the double bond can go on either of the oxygen, then you know the bond order would be like 1.5 because it's splitting the bond across both of the oxygens. We will go into some of those where it's not necessarily a whole number for bond order when we get to drawing the Lewis dot structures. Now, higher bond order means you're stronger. And you also have a shorter bond length, okay? So as the bond length gets shorter over here, bond strength, of course, is equivalent to shorter length. So triple bonds are actually the shortest of the bonds, and single bonds are going to be the longest. Okay, in terms of the length. So if you have a longer length, your bond is going to be weaker. The shorter one is going to be stronger. And of course, double bonds fall in the middle of these general categories. But this is all relative because the size of the atoms also play a little bit of a role here in determining the bond lengths, because you know that some atoms are a lot larger than others. So atomic size and bond length, the atom size decreases across the period and increases down a group. You remember that? So larger atoms increased bond length. And I gave you this chart of comparing the bond energies with the length. And as you can see, you should see patterns. For example, if you're looking at, say, silicon right here with all of the halogens, what you should notice here is Si to F. The bond energy is 565, which is incredibly high for a single bond, but we know fluorine is super attractive because it's got such a high electronegativity, and it's really small in comparison. So its bond length is 156. As you go down the group, the energies go down, but that's because the bond lengths are increasing. Okay, and also there is that special note that, like I said, fluorine is super electronegative, very strong, holds on to the bond, attracts in those electrons. That is another factor, but it's also really small, so its bond length is going to be smaller. So you see that particular trend in a bunch of the ones. If you look down groups, see how they interact with the different groups. For example, see here, going, say, across a period. So you have carbon to carbon, carbon to nitrogen, carbon to oxygen. So going across the second period there, if you see here, carbon to carbon, the energy 347. Its bond length is 154. This is interesting. This one's only 305, so like I said, doesn't always fit exactly the trend, but it does have a shorter length, so a little bit less energy there, and that might be because there's a little bit more repulsion going on. And then the C to O is definitely the strongest, and its bond length is the shortest. Okay, that's because as you go across the period, carbon is the largest, then nitrogen is in the middle, and then oxygen is the smallest out of those particular atoms. Now they're just slightly different in size, because remember it's all of the difference of one proton being added. But and I wonder if this one has anything to do with like the ionization energy and where the electrons are fitting into the orbitals, because we have that particular issue there. Actually, no, that would be for the electron affinity where they're going into the orbitals, as to why that one doesn't necessarily fit the trend, but you're going to base it off of just the trend, because they're not going to give you these numbers every time. Sometimes they might give you a chart of numbers to refer to and get your data points off of those. Sometimes you just have to do it relatively off the periodic table. So keep that in mind. So you're going to place the following in order from strongest to weakest. I want you to do both exercises for that, and then we will go over them in a few minutes. Okay, place the following in order from strongest bond energy to weakest bond energy. So really, what you should look at here is, first thing you should notice, all of them are single bonds and all have a bond order of 1. So you really can't compare it based off of bond order. What you want to look at though, now if they all have the same bond order, is the size of the atoms. So you're looking for bond length, relative bond length. They all have carbon in them, but as you notice, they give you a trend, which they're all attached to a halogen. So they're in the same group. Out of the halogens, fluorine's the smallest, bromine is the largest, okay? Chlorine's going to be in the middle. So we want to do the strongest to the weakest. The strongest is going to be the one that has the shortest bond length, which is going to be the one with the smaller atom. So that's going to be C to F, right, is the strongest. Then comes C to Cl, and C to Br would be the weakest because this is the largest atom. So its bond length will be longer. All right, so that's how you're supposed to kind of do these, especially if they don't give you a data chart with all of the bond lengths and bond energies. Now here, looking once again, these are all bond order 2 because they're double bonds in there. Strongest though, once again, should be the carbon with the smallest atom because they all have carbon in them. So which one is going to be the strongest? C2. Strongest? Which one's the smallest of the C, O, and N? O, so that's the strongest. Then comes, and the carbons are just the carbons are slightly larger, so that would be the weakest, like so. All right, now we're going to look at drawing on the free response. They'll have maybe one of these possibly in a multiple choice, but a lot of times I see it in free response where they give you the graph and they want you to draw in the other one, okay? So graph, this is one for bond order. Graph of the potential energy versus internuclear distance for C triple bond O here is given. So this is showing you and representing the C triple bond O one, okay? That's for this particular one. On the same graph, carefully sketch a curve that corresponds to the potential energy versus internuclear distance for C that's double bond O and C that's single bond O. So if I'm looking here and this one, the potential energy is way down here, its internuclear distance like so. The C double bonded to the O should be longer or shorter than the C that's triple bonded? Longer. Should be longer. And should it be stronger or weaker? Weaker, so it's not going to release as much energy, and the internuclear distance or bond length should be a little bit larger. So over here I should position like where the dip is going to be a little bit to the right, and I'm not going to go down as far, right? So I'm going over here, drawing it, oops, that's not really the best, but anyways, so it goes right here. So this would be the C double bonded to the O. Of course, make it a little bit more round here. Okay. Now if we're doing the C single bond O, where would that one go? Where would we want to draw in our curve? Over here to the right, because its bond length is even longer, and the dip should be shorter. So you would draw some, oh, my dip is not, well, I guess we can still work with that. Because it's over here a little bit, it's still longer, okay? And the dip here showing that less energy was released, so that means it is a weaker bond, okay? Now I think I drew it better on this one. Yeah, that's a little bit better. Where you want to make sure that when you're drawing them in, if it is longer and weaker, you go to the right and you don't dip as far. If it is stronger and shorter, you go to the left, make the dip go longer. Okay, so that's kind of how you do these. Now for the next one. You go ahead, sketch it real quick. See, well, we will come back in just a second. Okay, so I've heard some good discussion here. Yes, Cl2, bond length going to be longer or shorter than H2? Than H2? Should be longer. Remember, chlorine has 3 principal energy levels. Hydrogen only has the 1, so hydrogen atoms are pretty small. So the chlorine atoms in terms of size are going to be larger, so therefore their bond length has to be larger. So you would move it over here to the right, do your curve. It's not going to dip as far. Okay, I mean, obviously, like so. And they have done these many times on the FRQs, especially for the last like 5 years or so. So there's my one that I did on my iPad. All right, try this one. You have a graph potential energy versus internuclear distance for HBr, H2, and Br2. Label the lines that with their corresponding compound. Now the first thing you should think to yourself is which one is going to have the shortest bond and therefore going to be the strongest. And of course that one's going to go with which color? Blue, the shortest, strongest. So out of those, which one's the shortest and the strongest? H2. So we would do H2 here. And which one is going to be the longest? So that one should go with green. That's going to be the longest and it's going to be the weakest. And then the one in the middle, which is a combination of the hydrogen with the bromine, that one would be the middle type picture. Like so. Now let's talk about ionic compounds. And we'll talk about more of the properties in the next set of notes, but we're going to go into the detail of the actual ionic bond here. I like this particular graphic set of things because it shows you the lattices. And of course, sodium fluoride and sodium chloride are both 1-to-1 in terms of their +1, -1 arrangement. Once again, they form this lattice and they organize it so that they maximize attractive forces and minimize repulsive forces. As you can see, not everything follows a 1-to-1-to-1 because we have the CAF2 down here. And that particular pattern of how it builds its lattice is going to be different. And there's plenty of other patterns and arrangements as to how they construct their lattices. We won't have you, you don't have to know those or memorize those. It's not part of the scope of this course. But if you do go into more advanced chemistry in college, you might have to actually memorize those unit cells. And we'll talk about unit cells in the next set of notes briefly, just so you understand that the way that these patterns of the crystals build themselves, they're not always 1-to-1, like sodium chloride or sodium fluoride. Now, how do they come together and measure the bond energy of the ionic bond? Well, it's done through calculating and finding the lattice energy. The lattice energy is basically a measure of the strength of the bond, okay? Whereas we have the bond energies for the covalent on the table. Here, you're going to see the lattice energy. This is the energy that's released when the gaseous cation and the gaseous anion, they come together, form the bond. Forming is warming, so they release this huge amount of energy. And that's what is known as the lattice energy. Heat is emitted, forming is warming. We're going to go over that. Now, extra stability that accompanies the formation of the crystal lattice is measured as the lattice energy. And they said stability because remember it's about getting to a lower energy state. So all this energy gets released, and that puts it in a nice, stable, lower energy state. How strongly the ions attract to each other in the solid state is indicated by the lattice energy. A larger magnitude of lattice energy, the more attractive force between the ions. So once again, how much is released is really equivalent to how much you would have to put in order to break the lattice bond or the ionic bond. Lattice energy is released when the solid crystal forms from separate ions in the gaseous state. This is always an exothermic process because heat's being released. Forming is warming. Hard to measure directly, but can be calculated from the knowledge of other processes. So lattice energy, as you can see, is very similar to Coulomb's law. Basically, it's still the magnitude of charges on the top, Q1 and Q2, over the distance. And it's not R squared on the bottom this time, it's just distance. So you can cite the lattice energy equation here when you're explaining the strength of an ionic bond for different compounds. You are never going to be asked to calculate it, but like I said, when you're trying to explain it, you can use this equation. You can use Coulomb's law too, because it really still is the magnitude of the charges and over the distance. Now they're saying the distance of the two ions to one another versus like if you're using Coulomb's law, the distance of the nucleus to the outer valence electrons, what we talked about in Unit 1. Still applying kind of the same concept. All right, bond energies. Before we get into looking at true lattice here, to break bonds, energy must be added to the system. It's endothermic. Energy term carries a positive sign. And how we try to remember this is we say axing is taxing. If you have to break it, which is like chopping it with an axe, breaking it takes energy. To form bonds, energy is released, exothermic, energy term carries a negative sign, and we say forming is warming. So if you form bonds or forces of any kind, it could be intermolecular forces, it could be ionic bonds, it could be covalent bonds. Forming is always warming, axing is always taxing. Now, if you're talking about a chemical reaction, which we're going to get into later, you have to break bonds and form bonds, and that's going to be the overall net that actually determines whether it's endo or exo overall. But in every chemical reaction, you have to break bonds, so there's some portion of it that's endothermic, and every part of a chemical reaction you have to form bonds, and that's going to be exothermic. It's just which particular part is larger will determine what happens for the overall reaction. All right, so the Born-Haber cycle demonstrates all the different steps of the lattice here, and you can look at the diagram, and you can even watch the short video here if you really want to. But you have a couple of different things occurring here. You have to change the solid sodium into gas. You have to sublime it. Then it has to go and change into a +1. So you have to use ionization and rip off an electron. The chlorine has to also, you have to break the bond between the Cl2 that's holding it together. Okay, and you also have to add an electron to it. So there's electron affinity going on. And once they become gaseous for sodium plus and Cl minus, then they coalesce together, release energy, and form the lattice energy. Here are the individual steps that are written in your notes. Those are easier to follow. Sublimation of the solid, endothermic. Once again, you have to add energy to overcome the forces that are holding the solid together. Ionization energy of the metallic, so you have to rip off an electron. Showing you here, you're breaking off. Electrons are attracted to protons, so you are overcoming forces there. Dissociation of the nonmetal, which basically is breaking the bond between the Cl2 and the previous one, it's breaking the bond between the X2. That is endothermic. The last two processes are exothermic, formation of the nonmetal ions in the gaseous phase. So you basically have to add the electron to, say, the chlorine or this X here, and forming is warming, so that's exothermic. And then when the two oppositely charged gaseous ones come together, it releases it quite exothermic. It's a huge amount of energy. So let's talk about that. All right, here shows you two examples. You have the NaF on this side, and then you have the MgO over here. And it's showing you all the different changes here. But this number right here, it's hard to see, it's negative. This number over here, these are both the lattice energies. So this is the EL over here, and this is the EL lattice energy for NAF, which is negative 923. What you see here is the MgO releases so much more energy. So the bond between MgO is a lot stronger than the bond between NAF. However, NAF still has a lot of strength in its bond. It's like a melting point is still high. It's like above 800, 900 degrees Celsius or something like that. But the MgO one is really, really high. It's like in the thousands. So more energy release in the lattice, okay? You're never going to have to calculate it, but this is just showing you graphically with all the steps of the Born-Haber process here. Like I said, you can go through all that detail, but it's kind of unnecessary. If you want further extension, though, you can look at it. What we really have to compare here is using our equation for proportionality reasons. So, lattice energy versus ion size. So we know that our EL, basically, yes, there's a constant, but it's Q1, Q2 over distance. And here, if you look at all of these, all of them are +1, -1, right? They're all alkali metals with chloride. +1, -1. So the Q1, Q2 arrangement here, that's going to be the same for all of these particular examples. What is different, though, is the different sizes. Lithium versus sodium versus potassium versus cesium here. As you can see, the cesium ion is the largest, so when it's paired up, it has the largest distance. So that affects the bottom here. If you're dividing by a larger number, your force is weaker, or your amount of the lattice energy is going to be less. Less number means lower bond energy, and the lattice energy is lower, that means weaker, because the force of attraction is weaker. And as you can see in the numbers decrease as the alkali metal ions get larger. Okay, so that's one thing to look at there. All right. Now trends in lattice energy for ion charge. Okay. Force of attraction between oppositely charged particles is directly proportional to the product of the charges. Larger charge means the ions are more strongly attracted. Larger charge, stronger attraction. Stronger attraction, of course, is a larger lattice energy, amount of energy released. Of the two factors, the ion charge is generally more important, or it is a bigger factor. Okay? This is +1, -1. This is +2, -2. As you can see, they are about the same size, but if we looked up, say, the melting point of the two different ones here, the calcium oxide's melting point is going to be triple that of the sodium fluoride. So the strength, the numerator here, the charges, actually plays more of a role in making the lattice energy higher, therefore making the ionic bond stronger. So let's look at some examples here, like the melting points for NaCl and NaF are given below based on the data. Which ionic compound has stronger bonds? Well, here, we want to look at our EL, Q1, Q2 over D. Both of these, this is +1, -1, +1, -1 in terms of their charges, right? Now, both of them have sodium in there, so this factors out, right? Those are going to be the same, so that doesn't matter. Now we have to look at distance. Fluorine versus chlorine, which one's smaller? fluorine is smaller, and as you notice, its melting point is higher. Higher by, almost 200. Okay? So the strength of this one is going to be greater because the distance here, smaller distance from the Na to the F here. Okay? In terms of the distance there. The melting point being higher means you need more energy in order to break up and spread out the particles. Okay? Now, if you're going to talk about this, of course, it's always good to refer to the equation, or you can use Coulomb's law too. So the higher one, of course, is the higher melting point is the stronger one. Using lattice energy or Coulomb's law to explain the magnitude of the charges for the same for both compounds. However, smaller ions, the closer they can get together. So you would say, since fluorine is a smaller ion than fluoride is a smaller ion than chloride, and the sodiums are the same, the distance between them would be shorter. The shorter distance means higher lattice energy, and you can refer to the lattice energy equation. Or you can refer to the Coulomb's law and say the same thing, like the distance on the bottom is going to make it so the smaller ion, these are ions, the smaller ion, of course, is going to have the bigger lattice energy or force of attraction. Okay? So that's one example there where they're giving you same charge. And this is usually how they set it up. They give you like the same charges, or they give you different charges and about relatively the same distance in terms of size of the ions. Like this one here, if you're looking at this one. Obviously, the melting point there of MgO is almost triple that of NaF. So which one is definitely stronger and is going to have stronger bonds? MgO. Okay? We look here. MgO has the higher melting point. Now, for comparing these, though, this is +1, -1, this is +2, -2, like so. Looking at the periodic table, though, sodium and magnesium are right next to each other. Sodium is a little bit larger than magnesium, not by much, very much so, right next to each other. And then we have fluorine and oxygen, so fluorine is smaller than oxygen. So the sodium, which is slightly larger, is with the smaller fluorine. The magnesium, which is just slightly smaller, is with the little bit bigger oxygen. So the size pretty much cancels itself out here. The distance is going to be approximately the same. But this magnitude of charge, that gives like a magnitude 4 times that, because it's 2 times 2, 4 times the other one, which is 1 times 1, or +1 -1. You know, yes, it comes out negative, but that's only because we're talking about attractive force and releasing energy in the process. Because if you're attracting, you're forming a bond, forming is warming, so you're releasing it, that's why the negative sign is there. So it's the same kind of concept using lattice energy or Coulomb's law. Fluoride is slightly smaller than oxide, magnesium ion is smaller than the sodium. Generally the same size here, or distance, same distance, you could put it as that. Magnitude of charge, the 2 minus and 2 plus have a greater attraction than the 1 minus and 1 plus. You would say that numerator, of course, affects the calculation of the lattice energy or the force of attraction, and that's why it has a significantly higher melting point.